Hello everyone. This video lecture is a continuation for the previous video lecture. In this video lecture, we'll be talking about the image processing techniques and followed by different types of images that can be processed using simple techniques. So in vision basics, we have fundamental image terminology. Those are binary operators, filtering, and edge operators. So using these three fundamental image processing terminologies, how we can process images is the ultimate aim of this lecture. First, we'll deal with the example of a digital image and then its terminologies. We have a particular pixel with a value of 19, and it is surrounded by a 3x3 neighborhood. And this is the region for like some intensity level, that is one part, and then the total image resolution. So using all these terminologies, how we can actually decide upon like which part to be concentrated for application of any one of these operators. So certain images we are not aware in previous part. So we have seen some basic fundamental formats for images like JPEG, GIF, etc., etc. But we don't know about multispectral image and then range images. These two are very much essential when you're dealing with a mobile robot, because multispectral images are something like you have different spectra of light radiations where you have to concentrate for an application. Like the best application part is like if you're planning to use a drone for detecting some anomalies in the crop area. So you fundamentally require different spectral data. For example, if some rodents that impacts the crop area and a particular region of the crop is damaged, so the spectrum of that particular region would change. So you can clearly concentrate upon like which region has been damaged and what kind of measures can be taken based upon the image. Range image is entirely like it depends upon like the depth part. So we'll talk these two concepts in the later slides of this video lecture. So you can visualize there is an entire region which is having some different terrain, which is fundamentally a flat region here, some like typical tree locations here, and then you have some altitudes here, and then certain crops that are already planted at different stages of their crop level. So you can visualize the same image is being described using different spectral data. So for example, this particular region of the crop could be like is ready for harvesting, or this part is already harvested, this is yet to be harvested, and it is somewhere in the mid of certain region. So this region has to be it is a very initial stage of a crop, and this is like the second stage of a crop, something like that. And these terrains are visualized in terms of like blue and all, which is water that is surrounded by a terrain. So using this multispectral image, what fundamentally we'll get is like what is altitude, so how does the color shift has impacted on the altitude, and then how color shift has impacted on typical regions like fully harvested crop, semi-harvested crop, etc. So this spectral data is used when you are typically having a camera that is being held at an altitude. Let us say a satellite image also can be used in the multispectral data part. The next one is the range data. Range data is very much familiar. So what you fundamentally require is the depth. So that can be easily obtained by a typical depth camera. The best example for this is Xbox 360's Kinect. So you have a depth camera there where the depth is processed by the IR range sensing, and the visualization would be something like this. So there are some color regions where the green represents it's an open area, and the black represents it's an obstacle, and the semi-blue represents obstacle that is located at a particular range. So range images are used when you want to process the realistic data, whereas this spectral image could be like it could be a part of post-processing as well. In most of the cases, spectral data is post-processing data. That is, your satellite takes an image, send back to your Earth station. Earth station will process and then tell the people that which region is having anomalies and all. But in this case, the data is more realistic, and you will get the depth as the robot moves. The depth information is captured simultaneously. And there are three fundamental stages in case of computer vision, which is a low level where you have an image, and this image The low level images could be like are processed with very fundamental things like filtering, then typical filtering and all. Whereas the mid level has the feature, and then high level will have some analysis. So using these three, how we can interpret an image, let us see in the upcoming slides. The low level is fundamentally like the best example for us, sharpening. So if you increase the intensity of sharpening, you will get a better quality image. Where you decrease it, you will get a blurred image. So sharpening is basically you highlight the regions which are most essential, and which are not essential you can blur off. When it comes to mid level, you can visualize something like this. That is a simple canny algorithm which is applied for getting the edges, and then ORT, whereas it has a typical optical resolution that will be carried out using a fundamental edge detection. So edge detection is fundamentally a mid-level operation, and different algorithms are used for edge detection. The best example for this is Canny, and here we have a typical data structure that defines only the circular part you can visualize in the ORT algorithm. We have a typical observance, so that is obtained from this edge image. So this edge image is further processed, and it will highlight the regions like circles. So here there are more number of circles you can visualize in the realistic image. So these circles are highlighted here. So that depends upon the data structure as well, like which typical data structure you are following for your image processing. Then in the mid level, you have a typical color image where you can follow some typical algorithm like k-means clustering, where all the components are interconnected to each other in this image. You can visualize there is a roof structure and the road which are almost of the similar color. So this regions will have a homogeneous color representation. So the data type or the data structure, whatever that is used, is like similar color regions which are processed using the mid-level image thing. So whatever regions that are occurred are being shown as red, and so the rest of the regions are shown as blue, green, and all. So these are, so fundamentally what we'll get the data is like so which typical areas I have to be concentrated the more. For example, if I am planning to target upon the windows, so I have to concentrate upon the color that is pertaining to the windows, so I can process only that region. So in the previous case we have concentrated upon the circles. In this case we have concentrated upon the surface. So that's a fundamental difference using ORT as well as a simple k-means clustering. In high level, we have images like the realistic image. So in this realistic image, the low level processing is applied. For example, basic filtering is applied whether to remove unwanted regions, and it could be black dots or maybe red spots on the particular image, and then followed by a mid-level application, that is mid-level processing, that is edge detection. And after edge detection, it has used some consistent line structures. That is, for example, you can visualize the windows. All windows are consistent line structures. So we can visualize, or we can estimate what is the number of windows, or what is the what do you call the difference between two windows, etc. In this case, so that becomes a high level image processing. It is a bit advanced here. So once the building is recognized, so you can make up a building model. For example, let us say in this case we have totally 5 cross let us say 6 windows. So using this number of windows, we can create a building model, and this model can be compared with your original model. So every time when it looks into a building, it will find out the windows and then the typical structure of the building. Not every building. So typical structure or specified data type has to be mentioned here. So like this is the way how these low level, mid level, and high level image processings are applied at in order to get a particular data set from an image. Some useful image processing operators are thresholding. You know very well about thresholding. A level of image intensity at a particular region is captured, and that is applied throughout the image, which is generally happens in a grayscale image. Determining good thresholds, like whichever the thresholds are good, so that images are said to be good because there is a uniform distribution of light intensity. And then fundamental morphological filtering, and then connected component analysis. Like connected components could be, for example, the roof and the floor both are connected in terms of color. So whenever there is an application of change in color here, so we can see a connected component which is a roof color is also changed. Then numeric feature extraction. Feature extraction, I need not to explain much because it is already discussed in the previous section, like how a particular feature can be extracted. That is, in this case, I can extract a particular feature called a circle. So circle can be a common feature that is present throughout the image. And then in numerical feature extraction, we have certain things called as location features. So location feature could be this thing, one particular location. And then we have gray tone features. Gray tone features are especially visualized in case of grayscale images. So one particular intensity region is considered to be a gray tone feature. And then shape features. So in this example, the shape feature also is considered. So let us move on to the next slide, which is the best example, which is thresholding. Thresholding is applied whenever you want to process some realistic images that are, let us say in this case, we are assuming it to be cherries. So a good cherry is bright always, and a bad cherry is like a medium dark in color, which has some bruises on it. So a threshold value of all these regions are captured by a image, and then it is shown on a histogram. If the histogram levels are not met with the standard one, so those cherries can be simply rejected. So that's the best example for thresholding. Then we have something called as mathematical morphology. Dilation is very fundamental mathematical morphology. So when you are defining dilation, it connects the set of zeros and ones in case of a binary image. So you can visualize this. This is a grayscale image. Binary image will have only two things. One is either black or white. So something like this histogram. So it connects the set of ones in a binary image, and then it can be used for developing some features that are growing features, then filling some features. In this example, growing feature is something like expansion of these edges in order to get the expanded view of a particular polygon that is here. Then something called as this filling gaps. So whenever an image is having some gaps which will bridge between two particular things, so that can be also done using dilation. This is also one best example. There is a non-uniform square here, so there are some unwanted regions that are present here which can be filled by using dilation. So dilation is useful when you are planning for filling up the thing. The second one is erosion, and then closing and opening. So erosion is it connects it, or it just shrinks up. It is exactly opposite of your dilation in case of growing features. It will shrink up this to the small one. So that is the erosion. Erosion is used for shrinking up the things. And the best example for this in case of mobile robots is that when you want to visualize an object that is present far away, so you can visualize only this part, not this part. So you can apply dilation on this, visualize this in a bigger form, and then determine whether this object is present or not. The best example for this is you're planning to drop a particular material at a particular region on the floor using a drone or something. In that case, the ground points are very nominal, which are very small and tiny in size. So use application of dilation here, and then you can find out the location, and exactly you can pinpointedly drop particular thing on that. Then the erosion is also used in order to remove the bridges, branches, small protrusions that are present between two binary connected sets. So in this case, you can visualize there is a bridge that is between these two circular objects. So that is removed here. So it will just remove those things using the edges. So only edge detection and erosion together is possible. In simple terms, application of edge detection is useful for erosion. Then structured elements. Structured elements is like a typical mask that is applied on a particular image. For example, you don't want the unwanted regions. You don't want certain regions that are present on an image. So you scan throughout the using this particular structured element, and then you can mask it. It is basically applied when you don't want a particular figure which is regular in size or maybe irregular in size. So you define the length and width of these particular elements, or you can just scan throughout the thing, so it will automatically eliminates the structured part. So that's the end of the day. So please have a look of this video and then be prepared for your exams. Thank you.